Dear students, I hope you are doing well. Today I will discuss with you crystal field theory. Well, it primarily deals with splitting of the electrons, splitting of the d orbitals in the transition metals. You have already studied transition metal chemistry in your FSc and in your BSc classes. You also have already studied writing of the electronic configuration of any transition element. I have also explained you how to write the electronic configuration of a metal ion and of a free ion. Here, for example, on this slide, you see the electronic configuration of titanium-2. It becomes a D2 system. All the rest of orbitals are completely filled. Well, here is the electronic configuration of carbon-6. These orbitals, as I have written them and as they exist in a given element, they are degenerate. It means they have same energy. Similarly, titanium 2 configuration and titanium 3 configuration. Titanium 2 configuration is a D1 system and titanium 2, as shown here, is a D2 system. The electrons, they fill up in the degenerate orbital. There are 5 d orbitals, 1, 2, 3, 4 and 5. 1 electron is here, 2 electrons are here. So that is how we write the electronic. When such like metals, they are hit by, or they are surrounded, or they are attacked by some species which has electrons, lone pairs of electrons, we call them ligands. When they are attacked by the degeneracy of these orbitals, that is lifted up. This is the whole thing about the crystal field theory. It is splitting of d orbitals when the ligands approach the metal. And I think you have already learned this topic to some extent in the transition metal chemistry and in the coordination chemistry. One of the key things which you have learned there is, of course, the splitting of d orbitals when they are placed in octahedral field or in a tetrahedral field. Here I have shown you a complex compound. In center is the metal ion, and this is ligand. This, and this. Ligand mean some species which has lone pair of electron. This metal contains empty orbitals in it, d orbitals in it. Those are filled by the electrons donated by the ligands. So here is structure octahedral and here is tetrahedral structure. Crystal field theory, as I have explained to you, it is nothing except that the d orbitals of a given metal, when it is approached by ligands or anions, okay, the degeneracy is lifted. This theory has been used very successfully for explaining the spectra of various transition. And note, the topic which I'm teaching you is also, okay, UV visible or electronic spectra of inorganic coordination complexes, and the crystal field theory explains it to some extent. We'll learn more details later on. This, besides spectra, it also explains the magnetic properties, and it wonderfully explains color of the complexes. Unluckily, I will not have much time to explain you how explains the magnetic property and color. This is just because of lack of classroom facility as well as time. Okay, I have to finish a good number of topics within the time period available. According to the crystal field theory, the interaction between transition metal and ligand arises from an attraction between the oppositely charged metal cation and negatively charged non-bonding electrons. So it is again purely electrostatic interaction. Metal is positive and ligand is negative, and there is attraction. The basic idea is that this ligand behaves like a Lewis base. Lewis means base is electron donor species, okay, and metal is Lewis acid. So interaction between an acid and a base. This is another way of understanding. And here I'm showing you ammonia molecule. It's a neutral molecule. It has these two lone pairs, okay, and cobalt 3 ion or cobalt 2 ion, or for that reason any transition metal ion, they all contain partially empty orbitals in it. Okay, some empty orbitals are available, some holes are available. So these pairs of electrons, they go to the metal, and as a result, combination between this, and it forms a compound. Here in this diagram, which when you might have seen in the material which I've already sent you, okay, this is ammonia, this pair of electron, okay, attacking the d orbital. This is d orbital. Ammonia attacking d orbital. Ammonia attacking. Now, please note, d orbitals have a directional character. This orbital which you see, this ammonia is coming right on the axis like this. So when this interacts, it goes up in energy. This is also axis. This is x-axis, this is y-axis, and this is z-axis. So all these ligands are coming on these axes, and therefore the orbitals on which the ligand is coming directly on the axis, it should go up. As the ligand approaches the metal ion, the electrons from the ligand will be closer to some of the d orbitals. Naturally, these d orbitals to which it is closer are the orbitals, axial orbitals. Axial orbit, that is dx square minus y square orbital and dz square orbital. And there are certain orbitals which are further away from other. So those are dxy, dyz, and dxz. The electrons in the d orbitals and those in the ligand, they repel each other due to repulsions between like charges. Thus, the d orbital closer to the ligand, again, closer to ligand are axial. Axial means they which come on the axis. This is z axis. This is x square minus y square axis, which are on the axis. They will go higher energy than those further away from the. This results in the splitting of d orbitals. Here I have shown the shapes of d orbital. It is given in the books. It is given if you Google crystal field theory, beautiful pictures of d orbitals are given. So this is the splitting now which is happening. These upper orbitals, they are being directly hit by the ligand. That's why they go up in energy. They are little further away, or there is not a direct approach. They are in between the axes. This is x-axis, and let us say this is z-axis, z-axis. So these orbital dxz, this is here, in between. So ligand is not approaching here. Ligand is approaching here. So this goes up, not this one. So here I have said the lower energy orbitals, dxy, dxz, and dy are named T to G set, while upper higher energy orbitals are called dx square and dz square. This is called EG set. This is group theoretical nomenclature. Each syllable and numeral has a specific meaning. Means T has a meaning, 2 has a meaning, G has a meaning. Similarly, E has a meaning, EG set. In EG set, okay, this one, E has a meaning and G has a meaning, okay, which I will just verbally explain to you. But the thing is, this is all group theoretical terms which we are using. And I usually teach this topic. I give 3-4 lectures, but right now it is difficult to do this. So all I am saying is you remember it as it is, that this splits up into T2G set and EG set. And what T and G means, I can explain it. Okay, T means triply degenerate. Look at this. 1, 2, 3, same energy. E means doubly degenerate. Look, 1 and 2. W means 2 degenerate orbital and 3 degenerate. Let us forget about what G means and what 2 means and what 1 means. Okay, most probably I'll send you some material on group theory later on. So this is the splitting I have shown of tetrahedral. In tetrahedral, this EG set is lower in energy and T2G set is up in energy. Okay, in octahedral, this was down in energy, this was up. In tetrahedral, it is just the opposite. The lower energy orbitals are named EG, while the upper energy are TG. Crystal field splitting of d orbital in different fields I am showing on my next slide. Okay, please, this is given in the books which I have already, chapters which I have already given you. You can go and see those. These are the d orbital, 5d orbital. This is T2G set and this is EG set. Okay, now please see this picture. This is octahedral. This is octahedral. In this distance A is equal to B. I have shown it. Here A is much greater than B. That means the ligand which is coming on the z axis, okay, the interaction between that is weakened, so this is stabilized. dz is stabilized, meaning it will go down energy, and you can see, okay, here it is here together, okay, dz square and dx square, but now it has come down. Okay, similarly, these two orbital in which there is a xz and y, they should also go down, and the other should remain up. So as this distance goes up, the shapes, it goes like this. So the other is this free ion, this is tetrahedral, and this is octahedral, and this is the whole thing which I needed to explain to you. Okay, well, I think I have communicated with you on next week this vagara vagara, but I think this is all which I want to explain to you on the crystal field theory. Well, I am so sorry. Okay, I do not have enough time to give you details about many other things which I usually cover in classroom. It is difficult. All you have to remember is there is a splitting when the ligand approaches, and the splitting happens because of the directional character of the d orbital. Some d orbitals are right on the axis, x-axis, y-axis, and z-axis. Other d orbitals are in between the d, and naturally they should split when there is a directional approach. If the ligands approach on the axis, then those orbitals will go up in energy. This is the whole concept of crystal field theory. Thank you for your attention.